Welcome to today's lecture on estimating latent heats. In the last lecture we talked about the different aspects and fundamentals related to phase change processes. During that time we looked at some of the latent heats or heat of vaporization and heat of fusion and so on. We used values which were directly obtained from the tables. However, in some cases such data might not be readily available. What do we do then? We need to estimate these latent heats using different correlations, and in today's lecture we will actually talk about what correlations can be used and how to apply them and what values you would be getting at. So, latent heats are usually measured by experiments. The data usually is obtained from tables. However, as I said, in many cases such value is not readily available. When data is not readily available in tables, you would have to use many correlations that are available. So, we will look at some of the correlations which can be commonly applied. So, the first and the simplest correlation that can be used is the Troughton's rule. This is used for estimating the standard heat of vaporization. Heat of vaporization for nonpolar liquids can be given as 0.088 times boiling point, and for water and lower molecular weight alcohols it can be calculated as 0.109 times boiling point. Here the temperature for the boiling point has to be used in Kelvin, and this will give you the heat of vaporization within about 30% error. So, this is not the most accurate method, however, it is the simplest thing to use. If you are looking for calculating the heat of vaporization to a more accurate level, then you should use the Chen's equation. As you see, the Chen's equation is a lot more cumbersome. It uses the boiling point and critical temperature in Kelvin and critical pressure in atmospheres. Tc is the critical temperature, Pc is the critical pressure, and Tb is the boiling point. This gives the value for heat of vaporization in a more accurate fashion. There is only about 2% error when Chen's equation is used. So, this is a good correlation to use. However, you need information not just about the boiling point, but also about the critical temperature and critical pressure for the liquid you are looking at. Clapeyron equation is another equation which can be used to estimate the heat of vaporization. So, this uses the vapor pressure data to estimate the latent heat of vaporization. Ln of P star is equal to minus delta H cap V by RT plus B. Assuming delta H cap V is a constant over a range of temperature, including in the vapor pressure data given, you can estimate the delta H cap value by plotting ln P star versus 1 by T. So, this would give you delta H cap V divided by RT as the slope. So, from there you can calculate delta H cap V, which is the heat of vaporization. In many cases heat of vaporization is not a constant for a range of temperature, it varies with temperature. So, in such scenarios the Clapeyron equation which we just saw is not directly valid. So, instead you can use something called as the Clapeyron equation, which is a differential form of the Clapeyron equation. So, d of ln P star by d of 1 by T equals minus delta H cap V by R. So, you are expected to plot ln P star versus 1 by T, and you would be determining d ln P star by d 1 by T as the slope of the tangent to the curve at the temperature of interest. So, as the slope changes, the delta H cap V would also change, indicating the change in heat of vaporization as a function of temperature. So, this delta H cap V can be calculated using the Clapeyron equation by plotting this curve and finding the slope of the tangent. Watson's correlation is another correlation that is used for estimating the heat of vaporization at a temperature different from the temperature for which you already have the heat of vaporization. If you have the heat of vaporization at temperature T1, you can calculate the heat of vaporization at a different temperature using the Watson's correlation which is given here. Again you would need to know the critical temperature which is for the component involved. So, you also have approximate formulas for estimating standard heat of fusion. So, you have standard heat of fusion for metallic elements as 0.0092 times melting point, and for inorganic compounds as 0.0025 times melting point, and for organic compounds as 0.050 times melting point. So, all the melting points used would be in terms of Kelvin. So, here are a couple of example problems where we will try and apply these equations to calculate the heat of vaporization or the heat of melting. The first example is the normal boiling point of methanol is 337.9 Kelvin and the critical temperature for this substance is 513.2 Kelvin. Estimate the heat of vaporization of methanol at 200 degrees Celsius. Now, what we have is the boiling point and the critical temperature only, and we have been asked to calculate a heat of vaporization at some temperature which is 200 degrees Celsius. So, this means we first need to identify and quantify the standard heat of vaporization for methanol, which would be at its regular boiling point, which is the boiling point has been identified as 337.9 Kelvin. So, this can be obtained either using Troughton's rule or Chen's equation. For Chen's equation, we need critical temperature and critical pressure. However, critical pressure has not been given to us in this problem. So, using Troughton's rule would be the simplest thing to do to get the heat of vaporization, although it is not the most accurate way to get the value. If we have the critical pressure value, we could have used Chen's equation to get a more accurate value for heat of vaporization. Let us now perform the calculation for heat of vaporization using the Troughton's rule. So, Troughton's rule had multiple equations. We had one equation for, so if you see this equations for Troughton's rule, you have two different equations, one for nonpolar liquids and the other for water and low molecular weight alcohols. So, here in this example we have to measure the heat of vaporization for methanol, which is a low molecular weight alcohol. So, we would use the second equation, which is delta H cap V is equal to 0.109 times boiling point. So, here the boiling point is 337.9. So, it is 0.109 times 337.9, giving us delta H cap V as 36.8 kilojoules per mole. So, now we have the heat of vaporization at its normal boiling point. However, we have been asked to calculate the heat of vaporization of methanol at 200 degrees Celsius. For doing this, we would have to use the Watson's correlation. So, Watson's correlation was delta H cap V at temperature T2 would be equal to delta H cap V at temperature T1 times critical temperature minus temperature of interest divided by critical temperature minus temperature at which the heat of vaporization is known, to the power of 0.38. So, this would be 36.8 times 513.2 minus 473 divided by 513.2 minus 337.9 to the power of 0.38. So, using this we would be able to calculate the heat of vaporization for methanol at 200 degrees Celsius as 21 kilojoules per mole. So, performing the calculations themselves is not too difficult here. What is crucial is to identify which equations to use and use them appropriately. We will look at another example problem to illustrate how to use the appropriate equations. You are again asked to estimate the heat of vaporization for N-propyl benzene at its normal boiling point using Troughton's rule and Chen's rule, and you are asked to compare the results with tabulated values for this quantity. You are then asked to estimate the heat of vaporization at 100 degrees Celsius using Watson's correlation. No information has been provided to us. So, we would have to use some handbook or textbook to get the values for critical temperature, critical pressure and boiling point for N-propyl benzene, so that we can use Troughton's rule and Chen's rule. So, the tabulated value for heat of vaporization should also be looked at, so that we can look at how the errors are for these equations are. Looking up the table, we can get the standard heat of vaporization for N-propyl benzene as 38.24 kilojoules per mole. So, Troughton's rule can be used So, here it would be 0.088 times boiling point. The boiling point for N propyl benzene can also be looked up the table, and the value is 159.2 degrees Celsius, which is equal to 432.2 Kelvin. So, using this value we can get heat of vaporization from Troughton's rule as 38.03 kilojoules per mole. So, for this particular case Troughton's rule seems to fit very well. You get very small errors, and this is as good as it gets, it is actually less than 1% error. So, even Chen's rule might not have this accurate a data. So, the Chen's rule can be used for calculating the heat of vaporization using the boiling point, critical temperature and critical pressure. So, the critical temperature for N propyl benzene is 638.7 Kelvin and critical pressure is 31.3 atmospheres. So, we would have to use these values in the Chen's equation, which is delta H cap V equals temperature of boiling point times 0.0331 times boiling point divided by critical temperature minus 0.0327 plus 0.0297 log of critical pressure divided by 1.07 minus temperature of boiling point divided by critical temperature. So, substituting the values we would get 432.2 times 0.0331 times 432.2 divided by 638.7 minus 0.0327 plus 0.0297 times log of 31.3, which is the critical pressure, divided by 1.07 minus 432.2 divided by 638.7. So, solving this equation we would get delta H cap V as 37.49 kilojoules per mole. So, for this particular case we find that Troughton's rule is more accurate than Chen's equation. Chen's equation here gives still less than 2% error. So, what we need to realize is, although Troughton's rule is perfectly fitting for this particular scenario, it can give up to 30% error. However, Chen's equation will consistently give less than 2% error. So, using Chen's equation can potentially give you a higher accuracy compared to Troughton's rule in more frequent analysis. So, the next step is to calculate the heat of vaporization at 100 degrees Celsius. So, for this we would have to use the Watson's correlation. So, the Watson's correlation is delta H cap V at temperature T2 equals delta H cap V at temperature T1 times critical temperature minus T2 divided by critical temperature minus T1 to the power of 0.38. Substituting the values we have, so we will use the more accurate value in this case, which is Troughton's equation, and which is 38.03 times 638.7 minus 373.2 divided by 638.7 minus 432.2 power 0.38. So, this gives delta H cap V at 100 degrees Celsius as 41.84 kilojoules per mole. So, with this we have used the different equations. So, again the example problems only looked at heat of vaporization. You can also do similar things with heat of fusion. So, I hope you would be able to practice more problems and get yourselves familiarized with these concepts. So, in case you need to estimate these heat of vaporizations instead of looking up, you would be able to use these correlations and actually get reasonably accurate values. With that, I would like to thank you, and we will see you in the next class.